All right, guys, Mr. Janowski here. Here is Chapter 10, Homework 2, Problem 2. So Alice gets on a carousel ride, so one of those merry-go-rounds with the horses that go up and down. Her horse is 5.5 meters from the center of the ride. The ride starts from rest, and after 8.25 seconds is traveling at top speed, making one revolution every 12.5 seconds. So A, what is the ride's angular velocity at top speed? So let's do, as soon as I can find my cursor. Oh, sorry, there's a little bit of a lag between me writing and it showing up, and I'm very annoyed at that. So anyhow, what is the ride's angular velocity? So angular velocity is what we're looking at. Give your answer in revs per minute and radians per second. So we're looking for omega equals question mark revs per minute, which you can just write as RPM, and we also want omega equals question mark rads per second. For part B, what is the ride's angular acceleration when it gets to top speed? So angular acceleration, the symbol for that is alpha. It looks like a fish. So alpha equals question mark, and the units for that, we're going to use radians per second squared. Sorry, radians per second squared. Part C, what is Alice's angular displacement? So another word for angular displacement is just angle. So yeah, linear displacement is just how far you go. Angular displacement is just the angle you go through. So the symbol for this is theta. Theta equals question mark. And let's do this in radians. And D, how far does Alice travel while the ride is getting up to speed? So how far means a distance. And in this case, because she's going in a circle, distance is really the same thing as arc length. The symbol for which is S. So that's S for arc length. I don't know why it's S for arc length, but it is. Not S for seconds. So that's question mark. And how far will the units of that be? Well, that'll be a meters thing. So let's start with part A. So what is the ride's angular velocity at top speed? Well, we know at top speed it's making one revolution every 12.5 seconds. So that is an angle per time. So we're actually almost there already. So our angle is, let me write it this way. Omega is delta theta over delta t. Okay, so what is our angle? Our angle is 1 rev, that is a unit of angle. And it does this every 12.5 seconds. Okay, now first we want this in revs per minute, which means we want to get out of units of per seconds, seconds on the bottom, and into per minutes. So I need field goal posts that get rid of seconds on the bottom and give me minutes on the bottom. So field goal posts, seconds on the top, minutes on the bottom, and remember the top thing needs to equal the bottom thing in different units. So how do seconds and minutes relate? 60 seconds and 1 minute. Okay, so let's see, the per seconds cancel, and the units we have left are revs over minutes. Well, that's revs per minute. That is RPM. So plug that into the calculator, and what do you get? You get 4.8 revs per minute. So I'll actually write it this way because I know what's coming next. Revs per minute. You could also write it RPM is usually how we would write that. But the next thing we need is to turn this into radians per second. So let's go from here with more field goal posts, get out of revs per minute and get into first radians per minute. So what field goal post would get me out of revs and into radians? Well, I had revs on the top, so my field goal posts need revs on the bottom and radians on the top. So how do radians and revs relate? 2 pi radians is 1 rev. So if I did this from here, my cursor has disappeared. I hate it when this thing gets laggy. Okay, there it is. Revs and revs. So if I did this now, I would have my answers in rads per minute, but I actually want my final answer in rads per second. So I need to get out of per minutes and into per seconds. So this is the opposite of what we did over here in the first part. So I had minutes in the bottom, which means I need minutes in the top in my field goal post, and I want seconds in the bottom. And how do these relate? 1 minute is 60 seconds. So per minutes in the bottom cancels with minutes in the top, and the units we have left are radians per second. So if I do this, my answer will be in radians per second. So 4.8 times 2 times pi times 1 divided by 1 divided by 60, what do we end up with? 0.503 radians per second. All right, sloppy. Okay. So yeah, we solved for the right thing. We gave it the right units. Probably should have done that over here. At this point, we also solved for the right thing and gave it the right units. So yeah, step A is done. Step B. That's a nice green. Step B, what is the ride's angular acceleration as it gets to top speed? So this is one of the ones where we're going to use the idea of cousins. So think of first, what's your basic definition of regular acceleration? We've been doing that for a while. Regular acceleration is change in velocity over change in time. So angular acceleration, the cousin of acceleration, must be change in the cousin of velocity. Well, the cousin of velocity is angular velocity, omega, over the cousin of time, which is still time. All right, so delta anything is going to be final thing minus initial thing over delta t. I'm going to leave that alone. The final thing, well, we just figured that out. That is 0.503 radians per second. What was the initial velocity? Well, the carousel wasn't spinning, so the initial angular velocity was 0. So finally we have let me undo that. So finally we have omega final over delta t. So that is 0.503 radians per second divided by how much time does it take this thing to get up to speed? Be careful, there's 2 speeds in this problem. Where's my cursor? There it is. All right. It takes 8.25 seconds for this thing to go from not spinning to spinning at top speed. So that's the time you want to use. You don't want to use the other one. The amount of time it takes it to go around once is not the time we want for this one. So ask your calculator, 0.503 divided by 8.25, and it will give you 0.0609. And what are your units? Radians per second divided by seconds. Your units will be radians per second squared. So put a box around it. Do step, we solved for the right thing. We did solve for alpha. And did we give it the right units? Yeah, radians per second squared. So that's good. Part C. This is going to be the long part. Where's my cursor? There we go. Now I want a purple. Give me purple. Not lavender, purple. Okay, part C. What is Alice's angular displacement? So this is the... Actually, let me bring that back down a little bit. Come on. Sorry. It takes me a while to get the hang of these controls here. Not at all what I wanted. Sorry, really hard to use this when your computer is getting really laggy. All right, I wish I could see all the numbers I needed. Yeah, part C. This is the kinematics part. So let's start here. Old-fashioned kinematics. You would do x initial, x final, v initial, v final, a, and t. So that's for linear kinematics, but of course, this is the thing with the cousins. So what's the cousin of x? It's theta. So theta initial is equal to, and theta final is equal to. The cousin of v is omega. So this gives us omega initial and omega final. And the cousin of a is alpha. Angular acceleration. And the cousin of t is t. T is its own cousin. So let's take it from the top. What angle did we start at? Just like usual, just call the first one 0. So 0 radians. What angle did we finish at? Well, that's what we're actually looking for. So this is going to be question mark radians. What omega initial? What was our initial angular velocity? Well, the carousel wasn't spinning. So initially, that was 0 radians per second. What was our final angular velocity? That was our answer to part A. 0.503 radians per second. What was the angular acceleration? Well, that was our answer for part B. 0.0609 radians per second squared. And time. How long did it take for this thing to get up to speed? So again, make sure you're grabbing the right time. The time we want here is the time from when this thing started spinning to when it got up to top speed, and that was 8.25 seconds. And I should be good and consistent and label these things. These are step 2. I'm skipping step 1. You know what? Say what? Here's step 1. Step 1. We had a carousel and it wasn't moving, and then it was moving. So there's your sketch. Step 3. Which thing are we solving for? Clearly, we were solving for this thing. This is the only thing with a question mark. Step 4. Pick an equation. Your equation has to have a theta in it, and it has to avoid the other question mark. So of your kinematics equations, 1, 3, and 4 all have thetas, and there's no question mark to avoid, so we have all the other ones. So you can use 1, 3, or 4. I find it's often easiest to use equation 4. So, as usual, just copy the equation exactly how it's given to you. Start there. You will make fewer silly mistakes if you start there. So 1/2 omega final plus omega initial times t. Any useful zeros? Yes. Omega initial is 0, which means we can get rid of this guy, which means we have delta theta is 1/2 omega final times t. So step 5, do the math. Get the thing you want by itself on one side. We already have that. And then at this point, we've got to go to the numbers. So 1/2 times 0.503 radians per second times our time, 8.25 seconds. Put that into the calculator, and you get 2.07 radians. So put a box around it. Oh, don't get laggy now, you stupid thing. Put a box around it. Do step, we solved for the right thing. We wanted the angle, and we wanted it in radians. So we're happy about that. And then finally, the last part. How far does Alice travel while the ride is getting up to speed? We'll go back to green. Let's pick a brighter green this time. That's too bright. That's probably close to the same green. Whatever. So how far does she travel? We're looking for distance, which is really arc length. Have we got a formula for arc length? We do. S is equal to r theta. So what's r? Well, remember, Alice is 5.50 meters from the center of the ride, so that's r. 5.50 meters. And what's theta? Well, that's what we just figured out. Theta is 2.07 radians. Remember, this formula only works, there's your decimal point, this formula only works when your angle is in radians. So ask calculator, what's 5.50 times 2.07? It'll give you about 11.4 meters. So put a box around it and give it a check. So, kinematics. They were difficult at the beginning of the year. Hopefully by now you've got them under your belt. It is always a little trickier when you're dealing with the rotational cousins than when you're dealing with the original things, because the rotational cousins are just that much harder to visualize. But hopefully with a little bit of practice, you'll see that it's not so bad. Hopefully that helped.